Hey, Dr. Clark here, and in this preview video, we're looking at Chapter 8.1, Intro to Linear Systems. Let's take a look. So first, just a quick reminder of why we would be looking at systems of linear differential equations. One application would be like nuclear decay rates or something. And, so here's a graph of all different radioactive elements, and then you can see, some of them are increasing, some are decreasing, right? And that's how radioactive elements work. One turns into the next, which turns into the next, which turns into the next, and so you get all these different things. And if you were going to model that and try to predict that, you would need a system of differential equations, one differential equation for each radioactive element. And then they would be interconnected with each other. So that's the kind of thing we have in mind. But we've also done salt tank problems where you have multiple tanks connected to each other. That's the kind of thing we're moving towards here in systems of linear differential equations. Now, it turns out in order to solve these, we're going to end up using a lot of things from linear algebra, so especially things with matrices. So the first thing is, what does a matrix vector multiplication look like? So a matrix is just a sort of a bracket of numbers, so 1, 2, 3, 4. A vector is just a column of numbers, so a matrix, and we're going to be using square matrices in this class, but you can have other kinds of matrices. And the way you do multiplication with a matrix times a vector is you sort of take the vector times the row. So 1 times 5, 2 times 6, so that's what? 5 plus 12 is 17, and that goes into the top row. So the column times the row, and then the column times the second row would be what? 15 plus 24 is 39. So this is how do you do vector multiplication for this particular example. But what it's going to look like for us is oftentimes some given matrix times a vector of unknown quantities, say xy. And so when you do the matrix vector multiplication, you get something like 1x plus 2y in the top row, and then 3x plus 4y in the bottom row. Okay, so most people have seen matrices before and vectors before, but if you haven't, this is sort of the main idea that we need to know. Of how do you multiply a matrix times a vector, and that's how you do it. Okay, so the next thing is, what is a matrix multiplication actually doing? Like, why does 5, 6 end up at 1739? Okay, and so I want to jump over quickly to GeoGebra just to illustrate this. I've entered the matrix 1, 2, 3, 4, and I've entered the vector 5, 6, and so here's the vector 5, 6, right? It just goes from 0, 0 to that point. When you multiply, so I've defined W to be the multiplication of A and V, you get 1739, and that is, I guess, way out there. Okay, it's much longer. So it turns out that this matrix is stretching this vector. It made it longer, for one, but it also rotated it. Okay, and that's what a matrix does. It stretches vectors and it rotates vectors. So it's two things. And if you have a different matrix, you would have gotten a different stretch and a different rotation, but also if you had a different vector. So here's a different vector, for example, U. If you multiplied that one times A, you would get, I called it U2 in this case, which would be way up there. But I've made U to be something that I can play around with. And you can see here that, the shorter U is, the shorter the multiplicated U2 is. But also, like, when U's over here, then U2 is over here. But if U is over, here, then U2 is down there. And there's even a place right about here, I guess, where U and U2 are in a line with each other. And that's going to turn out to be really important. This property is going to be key, figuring out for a given matrix, when will those vectors align? When will they be orthogonal? Oh, they lined up again, right? So there's kind of these interesting properties, right, where you started with U and it rotates and stretches it around, right? And sometimes it stretches it more than other times, which is it's just kind of cool. And if I had a different matrix, it would look differently, okay? And it's going to turn out that this idea is going to allow us to solve differential equations. So in the background is going to be differential equations, but in the foreground is going to be a bunch of linear algebra stuff with vectors and matrices, and how does a matrix rotate and stretch a vector for different vectors. And what the idea will be is if U is in a certain position, so let's say we've got 40 grams of uranium and 20 grams of plutonium, then the differential equation would say, well, 10 minutes later, you'll have this many grams of plutonium and this many grams. Now, in that case, they should be probably decreasing, so I should have probably gotten a matrix that shrunk the vector down instead of stretched it longer. But what we're going to see is the differential equation will create the matrix, and the matrix will tell you how does the state evolve in time. Another way to think of it is if x is position and y is velocity, then here we're all position and no velocity. Here we're all velocity, no position. You can imagine a spring kind of going around in a circle. You know, it's stretched to the right, now it's moving to the left, now it's stretched to the left, and now it's moving to the right, or something like that, right? It's sort of like going around, like the vector's moving around in what we call phase space, which is telling you the position and the velocity at the same time. So all of these problems, even that spring mass problem, can be recast as a matrix vector problem, and we're going to be able to use matrices and vectors to solve those differential equations. Okay? So the main idea, if I want to summarize this, is we're going to start with some system of differential equations that we want to solve, or, and we'll talk about this later, you can take an nth order linear differential equation and convert it to a system. So a spring mass problem is initially a second order linear differential equation. If we do a little math to it, we can turn it into a system of differential equations and then use what we're doing right now to solve it via a system. But once you have your system of differential equations, that will be converted into a matrix vector problem, and then we'll just learn a little bit of basic linear algebra to solve that matrix vector problem, and then we'll take that matrix vector solution and slap it back into the original context. So it's sort of like, oh, I've got this system of differential equations. We're going to go into linear algebra land to find an answer, and then we're going to come back into differential equations land and say this is what the answer to the original question was. So that's where we're going in Chapter 8. It'll take us a few sections to get all the way there, but we'll see you in class and tackle it then. Okay, so this is one of my favorite chapters. I think you're going to find it very interesting, and I look forward to working on some of these problems together.